All right. I have a wicked headache, and it's all your fault. So today, you guys were working on making those molecular models of small molecules, and I hope to actually have you guys complete it tomorrow. And so that sort of puts us a little behind, but that's not a big deal. So what I'm planning to talk to you guys today in the screencast is a little different than what it says on your syllabus. Don't worry, all will be well. We're talking about the concept of chemical reactions. We're moving into a whole new realm of chemistry, which is far more exciting and interesting than what we've covered so far. And understand that you actually deal with chemical reactions all the time. You just probably don't realize it. And so, for example, cooking is a set of chemical reactions, and burning wood in a fireplace is a set of chemical reactions. The gasoline burning in your car so that you can cruise it down the street. Walking is a chemical reaction of a whole bunch of chemicals inside your body. So chemical reactions are happening all the time, and you witness them all the time. But you probably haven't really thought about it in terms of formalizing a definition for the idea of a chemical reaction. And that's, of course, what chemistry is all about, formalizing. So you could write this down if you want to, but it's one of those things that's going to be such a natural part of your understanding that it might not be worth it to write it down. But a chemical reaction is a process in which one or more substances is converted into a new set of substances with different physical and chemical properties. So, for example, you start off with a chunk of iron, and if you leave it out in the rain and in the conditions of outside, then you're going to end up having rust. Not exactly sure what happened there. Something happened to the screencast, so I hope this works. But the rust I was talking about, it obviously has a different set of physical properties. It's red colored, it's more brittle than the actual iron that existed before that. But no, it also does have a bunch of chemical properties that are different too. Okay, so there are two parts of a chemical reaction. We have something called the reactants. In this case, it would have been oxygen and iron would be the reactants in the chemical reaction of rusting. And then we have an arrow which points towards what will be at the end, what will exist, which are called the products. So you're always going to have reactants leading to products. Okay. So there are actually two conditions that you need for a chemical reaction to actually take place. In other words, for this arrow to actually exist and move from reactants to the products. And those two conditions are pretty simple conditions here. One, you need to have atoms without a full set of valence electrons. And the reason that's the case is that if they don't have a full set, they're not going to be as stable. They're going to be more willing to look for electrons from other things or give away their electrons to other things in a reaction. And then the other thing that you need is very important here. You need energy to initiate the reaction. Okay, so those are two conditions. So let's take a peek at some of these, a couple of chemical equations. And chemical equations describe chemical reactions in this very reactants to products sort of way of doing things, of organizing things. Let's look at the breakdown of something like hydrogen peroxide. Hydrogen peroxide is the chemical that's actually created in your cells during cellular respiration, but it's also something that you can go to the grocery store, to the pharmacy, and buy a bottle of hydrogen peroxide, and if it's strong enough, you can use it to bleach your hair, if that's what you want to do. So let's take a look. Again, we're going to start off with our reactants, and in this case, the reactant we're looking at is hydrogen peroxide. Okay, and that hydrogen peroxide is going to break down, and it's going to break down to form water and oxygen. Now you'll notice a couple of things that I've put here. I've put the state of matter. So we're going to start off with hydrogen peroxide in its liquid form. That's an L. That's not an E. And then when it forms water, the water is going to be in its liquid form, but it also releases gas in the form of diatomic oxygen, which is in its gas form there. Okay, so that's a simple chemical equation. Now let's take a look at the one I was just referring to moments ago. I'm going to, I should probably go to a new page here. And that is creating rust. Okay, so that, oh, and keep in mind that it's very important that what I just showed here with the breakdown of hydrogen peroxide, that's one type of chemical reaction that can occur. And then let me show something where you actually have the buildup of something. And let's go back to what I was just talking about moments ago. You take a chunk of iron, which is a solid. Okay, you add in oxygen, and oxygen always has to be in a diatomic form. That's very important. And then that leads to having iron 3 oxide. Wait, am I right there? Yeah, iron 3 oxide, and which we know of as rust. Okay. All right. Now, there are different ways that we can classify chemical reactions. I've already talked to you about two of them. It looks like there was one that was a building up, one that was a breaking down. But we have a better way of looking at things, which is a little bit more specific. So let me start off with the first one. It's called direct combination. You should write these things down, by the way, folks, because we're going to be using these in the next lab at the end of the week. So we have something called direct combination. And in that case, this is going to look kind of like the rust that I just showed you moments ago. You're going to start off with a chemical A, combine that with a chemical B, and that leads to something where A and B are together and form the new compound. Right? If you, again, look backwards, this is what we have going on right here, direct combination. And also direct combination, if it involves oxygen, as this one did, we often refer to this as combustion as well. Now that may sound really strange. Let me just write this down, combustion. Because when everyone thinks of combustion, the first thing that pops into their mind is something that's explosive. But combustion need not be something that happens so quickly. So the reality is that rusting is actually a combustion reaction, even though it happens very, very slowly. Okay, then we have not just direct combination, we have something called a decomposition reaction, which is just the opposite of direct combination, and that's what we saw with this. The breakdown of hydrogen peroxide is a decomposition reaction. And so if we were to map this out in the format that I just used above, then with decomposition we start off with the thing that's in the combined state in the reactants, and then those reactants break down into the products where we have the separate A and B components. Okay. And there's no sort of also known as for decomposition. I wonder if I should show you examples, more examples of these things. Yeah. Oh, what the heck. I'll go ahead and throw another one. So let's say that we have something like ammonia. Oh, that's wrong. Ammonia is an N there. Okay, ammonia, not ammonium. Ammonium is a polyatomic ion. So we take ammonia, which is in the form of a gas, and we can break that down into its two components, nitrogen gas plus hydrogen gas. And actually, I put something in here that I don't want to put in. I just put a coefficient. So I want you to ignore the coefficients. Those of you who've done these before know that what I've just created here is totally not balanced. Now, don't worry about that if you don't understand the concept of balance yet. I'll go over that tomorrow in class or the next day. Just understand how to recognize a particular type of chemical reaction. So again, we have two so far, direct combination. I'm sorry, we actually have three so far, right? we have, what? Did I know? Oh, no, I don't know where I'm thinking. All right, so we had direct combination, then we have decomposition. The next one we have is something called single replacement. What color am I using here? Oh, blue. Okay. Single replacement. This is a little bit more complex in terms of what's going on here, but you'll be able to get it. We start off with an element. We combine it with some form of a compound, and that leads to switching of the A and B such that the A is combined with the X into a compound, and you leave B in its more elemental form. Okay? Typically speaking, not always, but typically speaking, this, oh, I meant to use the pointer. This dude right here and this dude right here are usually ionic compounds. So that means that A and B are also metals. Okay? So let me just write those two little notes. Am I doing notes in green? Yes, I am. Notes in green. So A and B usually metals, and either AX or BX are usually ionic compounds. Don't forget that. That's actually going to be really helpful for you to cheat a little bit later. And so an example of this would be taking magnesium, adding it to silver nitrate, which is something we actually have done in lab before, so this shouldn't be new. Oh, that'd be solid magnesium. This would be silver nitrate in an aqueous solution. And this would lead to, you're not going to be able to see the whole thing, a swapping. That's going to go on here. So I'm going to have Mg with the NO3. Notice that in order to balance this out, I needed two NO3s to go with my Mg, right? Because my NO3, my nitrate, is a -1, and my Mg is a +2. So to balance it out, I need to have two -1s to go with my 1 + 2 ion of magnesium. All right. In this case, silver is a +1, so it only needs one NO3 to balance that out. So the -1 and the +1 can come together to create the neutral compound AgNO3. And this also is a neutral compound of magnesium nitrate, MgNO3 2. And then let me finish this. So then you'd be able to produce, oops, like I said, I don't want to put in this. Okay, you'd be able to produce the silver, and then this would also be aqueous right there. Let me go ahead and move this dude. Oh, I didn't, what? I can't do that? Alright. There, that's better. Okay, so I want you to notice in this situation, a little hard to see, that the Mg and the Ag switch positions. Alright, here you have Mg in its elemental form, Ag is in the aqueous solution. Here you have Mg in the aqueous solution, and silver in its elemental form. Okay, again, that's single replacement. Okay, and then the last one we're going to talk about here. Unfortunately, I don't really have enough room, but I'll write it down here. And it's called double replacement. Double replacement. And a double replacement, if we're using the same sort of symbols here, oh shoot, I have to go and get a flu shot in just a second. You know what, I'm going to put this on pause and then come back to you guys and finish the last 3 minutes of the screencast. Alright, so I just got back from getting my flu shot. Whoopee, that was awesome. And so let me finish up this screencast I started. I only have a couple more minutes here. And let's see. What am I looking at? Double replacement. Right, double replacement. So with a double replacement reaction, it's going to look similar to single replacement. but make sure that you don't confuse the two because they are so similar. I want you to have your eyes open wide to see what's going on. In this case, you're going to have two compounds, two ionic compounds, and typically these two ionic compounds happen to be in aqueous conditions. In other words, they've been dissolved in water. And the A and the B both are metals, once again, just like we saw above with the green marks that I said up here. Right? A and B are usually metals. And it's actually it's simple once you get to this point because it's a matter of just swapping partners here, where the A then goes with the Y, and the B goes with the X as the products. Okay? So an example of that, I don't have a lot of room here. Let me squeeze it into here. So an example would be, say, take, oh wait, I don't want to do that. Undo. So I would take aluminum chloride, aqueous. I'd combine that with sodium carbonate. Oh wait, you know what, sodium carbonate doesn't need to have a parentheses there, so get rid of this. Oops. Sodium carbonate, which is also aqueous. And this would, again, the partner switching thing you're thinking about here, create aluminum carbonate, which actually precipitates out and becomes a solid, and sodium chloride. You know that is salt, and salt dissolves very readily in water. Okay, so there you have, there we go, boom. All right, so notice here that this Al right here will then combine with the carbonate here to form the aluminum carbonate. This sodium will combine with the chlorine here to form sodium chloride. And this is actually, it's sort of vital that you pay attention to the fact that this thing came out of solution or precipitated. So that is the precipitate that pops out of there. Okay, so there we have it. Those are the 4 different chemical reactions that exist. Actually, the ones that you need to know. We have direct combination, also known as combustion in some cases if you have oxygen involved. Decomposition, single replacement, and lastly, double replacement. So tomorrow, what we're going to do is we're going to take these reactions that we've talked about here, and we're going to make what are called true balanced equations. So that means the law of conservation of matter is in place to be sure that we haven't created or destroyed any matter, in other words, it's atoms, in the process of putting together these reactions. Okay, I'm stopping. Bye.